Okay, so till now we know what is crystallography, study of crystal. We know what is space lattice as a combination of imaginary lattice point in space, basis, groups of atoms or molecules which we place in those lattice point to get the crystal structure. Unit cell, it is a smallest possible geometrical figure which when repeated we get the crystal structure. Okay, then we know the lattice parameters. Who are this? A, B, C and alpha, beta, gamma. Then we know about crystal system. Crystal system, who are they? If we classify unit cell in terms of A, B, C and alpha, beta, gamma, then it is crystal system. If we talk about lattice point, are they only in the corner or corner plus body, corner plus faces or corner plus opposite faces, then that is Bravais lattice. So there are 7 types of crystal system we know in lecture 1, and we know there are 14 types of Bravais lattices. Then in lecture 2 we discussed about cubic unit cell in details, about the coordination number, the effective number of lattice point, packing fraction, relation between the radius of lattice point and lattice parameter A. These things we found. Now, is this sufficient? Now, can we say that we are capable to study crystals? No, we need to identify those planes. Okay, so crystals are not like it's not visible to our eyes that this is some plane there, this plane is rotating there. We cannot say that. We need some kind of technique to identify them. Like to students, we give some roll number for identification, right? And there is some rule to give those roll number also, like first 2 digit must be here, second 2 digit must be related to branch. So some rule is there. So this Miller indices is nothing but identification of crystal planes. What is crystal planes again? Plane we get by connecting lattice point. So that is crystal planes, and we have different shapes, different forms of crystal planes, and we need to identify those crystal planes by Miller indices. It is kind of roll number for lattice planes. Okay, next we need to find the interplanar spacing also. Then only we can go in our next lecture about extra diffraction. It is a technique. So before going to the technique, we need to make our theory strong. So interplanar spacing means those crystal planes we are getting, right, by connecting those lattice points, these 4 lattice points, another 4 lattice point here. So if we connect, this is one lattice plane, this is another lattice point. What is the gap between them? That is interplanar spacing. If we say international, means more than one nation involved. Similarly, interplanar means more than one plane involved. What is the space between 2 planes, or more than 2 planes also we can find. Okay, so we have to identify this plane and we have to identify this plane. Then we can find what is the gap between them. In this lecture, we are going to discuss about these 2 things basically. So first we should know what are the steps. Okay, then we'll do some examples. It's very important. So Miller indices, how they are defined? It is defined as the reciprocal of the intercepts made by the plane on 3 axes which have been reduced to small numbers. So if we just say the definition, we do not get the gist of it. We'll go one by one. Okay, so first what we have to do, then along x, y and z we have to find the intercept. Now many of you already know what is the meaning of intercept. Still, I'll just show you once. Suppose this is x, this is y. We draw a straight line. We know straight line equation is y equals to mx plus c. Class 7, 8, 9, maybe first time we learned all these things. M is slope, c is intercept. Who is this in this diagram? Here. This is c. That means this line y equals to mx plus c is cutting the y-axis at this value. This is known as intercept. So what we are going to do is we are going to find the intercept of the plane. Which plane? Crystal planes along x, y and z in terms of the lattice constant a, b and c. Once we found the intercept, we will take the reciprocal. This is step number 2. Then we'll multiply the reciprocal with least common denominator. If we do some example, it will be very clear. No worries. The next is the result is written in parentheses. This is called Miller indices in the form HKL. Okay, so HKL is just a symbolic. It can be 1, 2, 3, 1, 1, 1, 0, 0, 0. We'll see when we do the example. One important thing I will ask you to note here is you should never use comma in between them. It is just simply 3 digits. If you use comma, it becomes coordinate points. Like x and y, how do we write? If we have a point here, suppose 1, 0. then it represents a coordinate point of this point. So never use comma in Miller indices. Okay, just 3 digit within first bracket. Let us go on to find some Miller indices. We have two planes here in 3 dimension, x, y, z. First we'll do this one. Okay, this is example number 1, this is example number 2. So you see, along x-axis we have a cut here. Cut here means this is a, this is another a, from here to here a, from here to here another a. So how much? This is 2 along x. Along this is y direction, 1, 2, 3. So this is 3. Along z, 2. So what are the intercepts along the 3 dimension? Along x-axis it is the plane a, b, c. This is the name of the plane. This plane is cutting x-axis, y-axis and z-axis. Cutting means those are the intercept. So where it is cutting at x? At 2. Where it is cutting at y? At 3. Where it is cutting at z? Again at 2. Now what is the next step? You see here. Intercept we have to find. Step number 1 done. Step number 2, determine the reciprocal. So we have to take reciprocal. How we are going to take reciprocal? 2 reciprocal is 1 by 2, 3, 1 by 3, 2, 1 by 2. Then we have to multiply it with least common denominator. Denominator means what? This 2, 3, 2. They are the denominator, right? So you have to find the least common of this denominator. If we do this, 2, 3, 1. So least common denominator is 6. So everywhere we have to multiply with 6. This gives 3, this gives 2, this gives 3. So what is the Miller indices of this plane? Within bracket 3, 2, 3. Don't use comma, just within first order bracket the 3 digits 3 to 3. So you can say what is the Miller indices of this plane? 3 to 3. Okay. So now let us move to the other one, example number 2. Here you can see there is this unit cell rule. So that means this is 1. This is along y2. This is 1. This is also 1. This is also 1 along x, y and z. Now this plane is it cutting y-axis? Is it cutting y-axis? No. Is it cutting x-axis? Yes, it is cutting y-axis. Is it cutting z-axis? Yes. So now let us find the intercept. Along x-axis where it is cutting? At half. So our intercept is half. Along y-axis, is it cutting anywhere? It is parallel to y. So the rule for Miller indices, if it is not cutting any axis, what should we take the intercept? Intercept means cutting. Not cutting means intercept is infinity. Along z-axis, it is cutting at 1. So now we have to, next step is finding reciprocal. Reciprocal of half, 2. Reciprocal of infinity, 0. Reciprocal of 1, 1. Now what is the least common denominator? Denominator nothing means 1 is there everywhere, right? So 1, then our least common denominator if we take, it will be 1 only. If we multiply with 1, we are getting 2, 0, 1. So what is the Miller indices of this plane? 2, 0, 1 without comma. So one thing you must notice here, that whenever it is cutting at half, when the intercept is half, we are getting the Miller indices 2. Otherwise, if not cutting at all, we are getting the Miller indices 0. If it is cutting at unit length of A, B or C, we are getting the Miller indices 1. Okay. So this is an important feature in Miller indices. Whichever axis it is not cutting, the intercept is supposed to be infinity. Done. So this kind of practice you have to do more. By looking at the plane, you should be able to tell what is the Miller indices. So next, this one, last we'll do example number 3 also. For this one, can you do? So this is, you see, this is cutting only x-axis for this. It is cutting only if this is here x, y, z has changed. This is x, this is y, this is z. It is cutting x at 1, y it is not cutting, z it is not cutting. So what will be the Miller indices? Can we do without pen and paper? Yes, 1 reciprocal 1, infinity reciprocal 0. So Miller indices, definitely we are going to get 1 0 0. Okay, so these are some family of planes. You can see this one is parallel to Z. This is x-axis, this is y-axis, this is z-axis. This plane is parallel to Z, it is not cutting Z. So along HKL, first one is for x, second one is for y, last one is for z. So we are getting 1 1 0. Now this plane looks similar. Why you have written here 1 bar, here also 1 bar? What we have done, we have shifted our origin. Here this is our origin, now this is our origin. So if you see, it has cut x, yes, but on the negative direction. Negative means left along x. Along y, negative means back. Along z, negative means down. So up is positive, down is negative. Right is positive, left is negative. Front is positive, back is negative. Okay, so we have just plane looks similar, but the origin, maybe sometimes in various kind of exams they show the origin at different place. So you have to tell, okay, I know that this is not cutting Z, it is cutting X and Y, but since origin is in front, Y you have to go back, left you have to go left. Back and left means these are Miller indices is negative. So negative Miller indices, how do you write? We keep a bar above those number. Nothing, no negative sign in front of those, okay? We just use a bar there. So similarly, this second example, this is 1 0 1, 0 in the center. We should definitely understand, in the center 0 means it is not cutting Y. First is always about X, second Y, third is Z. So second one is 0 means it is not cutting Y. You can see here it is not cutting Y. It is cutting at X, it is cutting at sorry, this is cutting at X, this is cutting at Z, but it is not cutting at Y. Similarly, 0 1 1, instantly in our mind it should come 0 first means it is not cutting X. So this is our X, it is not cutting X, it is parallel to X. It is cutting only Y, here it is cutting at Y, here it is cutting at Z. So you have to look first where it is parallel. Okay, so that is one. So these are the important features, that if it is parallel means, see, two parallel lines, will they cut each other at any point of time? No. So the intercept is infinity in that case, and Miller indices become 0. So we have to look, next feature is we have to look into the origin and say whether this is in positive or negative. Okay, so these are some of the important features of Miller indices. Now let us find the interplanar spacing. This is the last topic of this lecture. So what we are saying, we have X, Y, Z direction crystal axis. We have a plane named as A, B, C. This plane is cutting at X also, Y also, and Z also. Yes, we do not know where it is cutting. We do not know, is it cutting at half of A, 1/3 of A, or full of A? We do not know. We just know their Miller indices are HKL. There is some identification is there. Now how to find intercept of this plane? So many of you have done maybe back calculation, you know the answer, you are finding from the back like that to solve some problems. Here also the approach is kind of same. See, Miller indices, how we find? First we find the intercept, then take reciprocal, then take multiply with least common denominator. So if we know a intercept, we can find Miller indices. By back calculation, if we know Miller indices, we can find the intercept. Okay. So from Miller indices, we are going to find the intercept. Let us look back into our previous this thing also. So this one, see, when Miller, this one, we know that is cutting at half of X. What is the Miller indices? 2. So if Miller indices is 3, it will cut at 1/3. If Miller indices is 4, it will cut at 1/4. So what we are doing, we are only dividing by the Miller indices. So Miller indices given HKL. What is the intercept along x-axis then? A by H, because H is along X, K is along Y, L is along Z. What is the intercept along y-axis? B by K. What is the intercept along z-axis? C by L. Okay, so now we know the intercept of the plane ABC. Now what we do, this ABC is touching XYZ, but it is not touching origin O. It is far from O. What we do, we draw a normal from O to the plane ABC. In this point P, it is 90 degree. At O, we do not know the angle. It can be 90 degree, it cannot be 90 degree. That is a variable, okay? So at P, it is always 90 degree. So this plane ABC, again I'm saying ABC is not touching the origin. From origin, we are drawing a normal to this plane and that we are naming it as OP. Okay, so I'm going to the next phase. So OP is making some angle with X, Y and Z axis. So this OP angle between OP and X axis is alpha. Angle between OP and Y axis is beta. Angle between OP and Z axis is gamma. So it is not necessary alpha, beta, gamma. You can take theta 1, theta 2, theta 3 also, no problem. As different books, it will be written in different way, don't bother. So here at P, it is always 90 degree. But along X, Y and Z, they are making angle alpha, beta, gamma. So this I will bring out one triangle from here, okay? So O, this is P, this is A. Yes? So we know this OA is intercept along x-axis. How much was the value? A by H. OA is A by H. OP value we do not know. AP value also we do not know. At P, what is the angle? It is always 90 degree, as I said, it is normal. What is the angle between OP and X? This is X only, right? OA. So this angle is alpha. So what will be the cos alpha value? Cos alpha we know is base by hypotenuse. I think some people say that as adjacent also, base or adjacent by hypotenuse. So who is the base in this for alpha? OP is the base. Who is the hypotenuse? Opposite of 90 degree. Opposite of 90 degree who? OA. OP by OA. So OP by OA. What will be the cos beta? You just draw out the triangle out like this. This one I have OPA I have drawn. No? Similarly OPB. This is OPB. So at P it is 90 degree. OB this is beta. So again cos beta if we find, it becomes OP by OB. And similarly you please find this one cos gamma. This will give you OP by OC. Now for every case, we know the value of OA, OB, OC. We do not know the value of OP. So what we do, see, we will draw another plane parallel to ABC, which is passing through origin. Similar, just similar plane to similar to ABC, but now this is passing through O. So one plane is passing through O, other plane is passing through P. OP represents interplanar spacing. Let interplanar spacing be D, HKL. Why HKL? Because Miller indices of this plane is HKL. So OP by OA is, OP means DHKL. OA means A by H. OP by OB, again D by B by K. OP by OC means D by C by L. C by L, B by K, A by H, how we got from the previous slide, you can see here, these are intercepts. In how we found? By just doing back calculation from Miller indices to intercept. Now if we do this, we are getting the value of cos alpha, cos beta, cos gamma. Maybe in class 10 or something you have studied about directional cosine. Since it is originating from a same point, so this cos square alpha, cos square beta plus cos square gamma should give you 1. This is by law, directional cosine. If we substitute the value of cos square alpha, cos square beta and cos square gamma, what were those? d by a by h. So this one we can write it as h d by a. This one we can write it as k d by b. This one we can write it as l d by c. So if cos square alpha plus cos square beta plus cos square gamma equals to 1, right? So everywhere d is common, d. Can we take the d outside? Yes, d square is common. H by a whole square, k by b whole square, l by c whole square, it gives you 1. So d equals to 1 by root of h by a whole square, k by b whole square plus l by c whole square. So this is the value of d. Okay, by using law of direction cosine. This is the general formula. So you see, if you take a cubic system means a, b, c all are equal. Let us say this is equals to a. In this case, what happens to this equation? Here also a, here also a, here also a. Can we take that common? Yes. In that case, d will be square root of 1 by, here 1 by a square common. We have h square plus k square plus l square. It is 2 times a denominator, so it will go to the numerator. Who? A. A square and square root cancel, will become a by root of h square plus k square plus l square. So sometimes students make mistake, they directly go to this until and unless the questionnaire asks you the cubic system. This is for cubic. Only when cubic, or like when they say that a, b, c all are equal, then only you go to this formula. This is a general case where you do not know what is the relation between a, b, c. May be equal, may not be equal. Okay. So D means what? Interplanar spacing. So in next lecture, we are going to discuss about Bragg's law and extra diffraction.